Welcome to Kenton Teaches. Enjoy the video.
You start by matching hardware limits with your kernel needs. Check the GPU compute capability and per block shared memory limit, then declare shared memory in the kernel using extern or static arrays. Once done, choose a block size that balances occupancy and shared usage, and pass dynamic shared bytes when launching the kernel. Make sure to align types and avoid bank conflicts by planning padding. This first step sets the foundation, so later reads and writes are fast and deterministic on the device. Next, you populate shared memory efficiently. Coalesce global memory reads into contiguous chunks and store them in the shared buffer. Once threads finish writes, use sync threads. To guarantee all data is visible, be careful not to call it inside divergent branches. Then perform your computation using the cached shared data, exploiting tiling and loop unrolling for throughput. Also add padding to eliminate bank conflicts, and consider register pressure versus shared usage, so you keep occupancy high while minimizing latency for interloop operations. Finally, write results from shared memory back to global memory using coalesce stores to preserve bandwidth. Once the kernel runs, profile occupancy, shared memory utilization, and memory throughput to verify gains. Adjust block size or shared allocation if needed. If things go wrong, first look for missing sync threads, calls, race conditions, or bank conflict patterns, and validate index math and alignment. Iteratively tweak tiling, padding, and launch parameters until performance and correctness stabilize, then lock in your kernel configuration.
Thanks for watching. Please subscribe if this video was helpful.